back to this live stream of real analysis. You see, we do the same as last time. We will solve some problems in real analysis, discuss them, and answer problems or questions from the chat. And the good thing is, fortunately, I don't do that alone. I'm here with Fabian again. Hello, Fabian.
Hello, everyone. Nice to be here again.
So how is it going, Fabian?
Yeah, it's a nice day. We have good weather outside, so I would say it's a perfect time to also do some math problems here.
Yeah. Always a good time to solve some math equations, some math problems. That's what we want to do.
Yeah, and I think it's also a very common mistake or something that people just that are studying or learning math do not frequently enough, is studying problems and solving problems the right way.
I would agree. Like, there are a lot of things you can do wrong while doing maths. And to be honest, we have seen that a lot from students. One thing I have in mind is that you can just read a lot, or can just print the lecture notes, something like that, and don't solve any problems at all. And then in the end, you see you don't understand the topic because the thinking was missing. The thinking of solving problems was just missing.
Yeah, it's also reading the same passages of the lecture notes or whatever you are using to gain this knowledge over and over again without understanding it better. And I think one way to always test your understanding is, can you solve a suitable problem with it? Do you understand the terms that come up in the problem? Do you know the definitions? And if not, then this is, I think, the second mistake that is then done, not going backwards. So don't be afraid to jump backwards in your lecture notes. If there's a term that you say, I learned this half a year ago, it won't be relevant or I won't need it. That's how mathematics works. You need to build and also refresh the foundations regularly.
Indeed. I think that would be a mistake, like missing repetitions. Yeah, you always have to do some things again. Yeah, it's just you will forget them immediately if you don't do it again. So also repetition of some problems. Sometimes it helps to do some similar problems just to keep it up, just to keep it fresh, to keep it in mind. And yeah, we want to do that here by solving problems. So I hope this helps. Maybe some idea how we see it. We upload these exercises beforehand, so you can already try to solve it if you want to participate here in the live stream. If not, I think it's also good to stop the video here and just try the exercises and then watch the solutions afterwards. Or how do you see it, Fabian?
Yeah, so I think there's also a third option, that is if you are not familiar with solving problems like this because you have not done one of these problems, would be to take a look at how you are supposed to solve the problems, and then this will be then the homework. Look for similar problems that you then can start to solve on your own, because I always feel that it's hard to get started if you have never seen someone just present you with the process of solving a problem.
Maybe that's also a mistake that can happen while learning maths. If you don't show your solutions, if you don't talk about it, because it helps a lot if you just present it or just talk to someone what you have done. And then you get feedback, and you also have to structure your thoughts in a way that other people can understand it. Yeah, so this is also important. Write down a solution and try to explain it to other people. So like we do it now here in some sense. Of course, we also do it live here, so it's a little bit, maybe a little bit more unstructured as it should be. I'm not so sure. Fabian, what's about your YouTube channel? You want to upload new videos?
Yeah, so I'm planning to continue the series on reacting or revisiting some of your functional analysis videos by enhancing or extending what you present, the definitions, the proofs, with some examples that you can always have ready or remember yourself of if you don't understand the topic. Because I think it's also, if you have a good example, if you know how an example works, then you may always extract some of the knowledge that you have from the workings of this example to a new problem that is presented to you. And then you can argue like this, it worked in this example, it could work like this again in here. And it's also a principle that one gains with practice.
You see general principles, general concepts with examples.
Yeah,
I guess. Yeah, I think that helps a lot, because if you see an example, it's much more concrete. Yeah, you can grasp the idea maybe more easily than with a theorem. So that's good. Yeah? I will watch your reaction video. So tell me about it.
Yeah, thanks. I'm looking forward to it.
Okay, I don't know if we should promise that we also will solve some functional analysis problems live, but I think that's something we could keep in mind and should do at some point.
Yeah, I keep that in mind, definitely.
Yeah, that would be more complicated or more abstract, because functional analysis is much more advanced than the real analysis we try to capture here. Yeah, because some people call this calculus, what we do here. But I don't think it's correct, because we also do more than just calculating. Yeah, so
yeah, we will also be doing some more abstract exercises again. So I think we try to mix calculations with proofs and arguments here.
Yeah, that's what I meant. Yeah. Like if you say calculus, you usually just mean, okay, here's a function, calculate a derivative. And yeah, we should also give the theory around that and try to solve abstract problems, or show a proof of some abstract statement. But we have some exercise for that, and I guess we should start with the problem 1 here, which is my problem. And yeah, I introduced this notation in my real analysis videos, and I use it often. So you need to know what the C2 or C3 means to solve this problem. And I would say we first define C1. So C1 of R. So this is a space, or first of all, a set of functions. So I could say, okay, this is a set of a function f defined on R. Maybe that's important to know here. This R here in the parentheses means the domain of definition. So now we do a real analysis. So we map into the real numbers. But maybe Fabian also knows sometimes you could also have complex values here, and you have the same notation.
It depends on the context.
Yeah, from context you have to know what we are talking about. Here we talk about real functions. So real valued, but important, the domain of definition is fixed. So it could be also an interval often, or just in another domain, but we concentrate on the whole real line now. Okay, now what do we have here? A function, and it is C1. So now we have a notion for that. We say this function is continuously differentiable. So what does it mean? Maybe that's a good question for the public, but of course, Fabian, you can answer it for the public.
It's 2 in 1. It means two things. It means, first of all, it's differentiable. And the second of all, so differentiable means we have a derivative, and then continuously differentiable means that the derivative is a continuous function. Again, and what you also know from your real analysis course is that the differentiable function is also continuous. So indeed, it's 3 things then that are meant in C1. We have a continuous function that is differentiable with a continuous derivative.
So differentiable means now this f prime, like differential quotient, exists at all points x.
Yes.
So this one exists everywhere. I just can write it down. Exists everywhere. This is one aspect. And the other one you also already explained, the continuous part here, means now that this f prime defines a new function because it's defined everywhere, but this is also a continuous function.
Yes.
So this is the second part, continuous. So this is important. because we have more information about f prime. So if we calculate with the function, we can also calculate with the derivative. And now we know two things. First, it's well defined at every point. So there's no question if this because it's defined over a limit. Yeah, so this is how we usually introduce this derivative. We have the limit. Now we talk about the definition in your problem again. So in problem 2. But then the question is, does it exist? And now, by definition of this function inside this set means, yeah, it exists everywhere. No problem. And we also have more. If we consider that as a function, it's a continuous function anyway. Oh, there is already one nice example in the chat. I think that's something you also had in mind, Fabian.
Yes, yeah, of course, there are always examples, and one of them is in the chat, of functions that are differentiable, but that do not have a continuous derivative. And yeah, some of them, some of the class of these examples always consists of a polynomial in x times a trigonometric function like sine or cosine with 1 over x in the argument. So something that oscillates very very hard going to x equals 0, but which is damped again by a polynomial. And yeah, this way you can construct examples that are outside of this class of functions.
Yeah. No, I like the idea very much. I have another idea to solve the problem, so we will discuss that soon. But first I want to define C2 and C3 as well. And now let me write something down, and then Fabian can tell me if this is useful or if it makes sense. So I can say, okay, C1 are now at least these functions we have defined before, continuously differentiable, but 1 times more. So I could say, okay, now this well-defined f prime is now also in C1. So it looks a little bit doubled, but just makes sense to say, okay, I go 1 step further. I go to the first derivative and say, now this is also in this C1, so also continuously differentiable, which tells us f2 prime exists and defines a continuous function as well. Yeah, so that would be one possibility to define that.
Yeah, I like it, because now you see what changes if you add 1 to the order of differentiation you have there. So now for writing down C3,
let's do that.
Well, you need to add 1 to every exponent in some sort that you have here.
Yeah, so this could be then in C2, and then I would say f.
Yeah.
Can I do it here? Like f2 prime is in C1 again.
Yeah.
So 1 step more again. So this would be C3. So now let's see if there's something in the chat. Yeah, okay, this is more or less my idea. That's good. Yeah, let's discuss some examples in the chat, and we discuss here the definitions first. Yeah, so what we want is now a function that is in C2, so that has the property that f prime is in C1, but it's not in C3. So f2 prime should not be in C1. So we could change 2 different things. Either this exists everywhere, but we don't have a continuous function. That was the idea Fabian told us about before. Or we can go just the easy way and just look at a function that where the derivative does not exist everywhere. Yeah, so it can just the problem can just occur at the first sentence here already. Good enough for us. Yeah, but not f prime, f double prime at this point. Yeah, because it should not be in C1. Is this correct? Yeah, f3 prime in this sense should not fulfill that. But we will see that now that we start. So we want a function where, oh, I need more space. So we want a function that is 2 times continuously differentiable, where the second derivative is not continuously differentiable. So, for example, should I write it down? For example, our f prime, f double prime, f prime prime, yeah, so count the primes correctly, should be a function that is not continuously differentiable. So in the common example I always have in mind, if I think of an easy function that is not differentiable, I just take the absolute value, because the absolute value looks more or less like that. So it has a linear function that goes into 0 here, and has a linear function that comes out. And the result is something that has a sharp corner here. Let's put it together. A very sharp corner here at the origin. So it's not differentiable at this point. So exactly what we want. It's differentiable at the other points, so no problem there. But not differentiable at the origin there. Okay, so now the chat. The chat says something about, yeah, looks good. Yeah, I think that's exactly what we will do now. So I don't have to ask a lot of questions for that, because that's exactly what I want to write down here. So this is how f double prime, the second derivative, could look like, because then it fulfills this condition. Yeah, it's still a continuous function, but it does not fulfill this one, because it's not differentiable. So then let's go one step further. So, should I define a new name? Yeah, maybe. Let's look at the antiderivative. I don't want to call it like that, but of course we have to go backwards now. So we could go backwards by saying, okay, if I do calculate the derivative of g, I could start with minus x squared and plus x squared, depending left or right. Yeah, and then we include 0 somewhere. So well defined. Also differentiable without any problem. Also at 0. Yeah, you can just calculate the differential quotient. You see it exists and it's 0. And now the graph. The graph looks nice in the sense that we have a parabola on the right. So this would be this parabola. But the other one is reflected. Yeah, so it looks like x to the power 3, but it's not.
Yeah.
It's not, yeah, because then we would not have a problem. But here, yeah, we don't see the problem of differentiability with the eyes so much. This bend we see, but then it's already hard to see higher orders of derivatives that it is a problem. It's not smooth enough in this 0. So
yeah. We see it because you have already the sketch of the derivative.
Yeah, there we see it. Just not in this picture. We don't see that differentiability one order more is broken. So we don't see it there. It's a little bit funny because we see differentiability is broken here. Yeah, okay. So it's just how good can you see smoothness with your eyes at which order? Yeah. So here it's very smooth because all derivatives exist, no matter which order, but not in 0. So yeah, we can just calculate the derivative and we get the absolute value by that times 2. Yeah, because of this derivative. But the times 2 is of course not a problem. The sketch stays the same. So the chat says something. Yeah. You can just tell me, Fabian, if there's something in the chat I should answer. Smaller or greater or equal than 0. And there we see, this is the absolute value times 2. Yeah, maybe I write it here. Plus 2 absolute value. Yep. If you want that. Okay, so now we already have the first step. Now we have to go one step more, yeah, because we want that this is f double prime. So for g prime, okay, so g prime should be f double prime. So we now have to find a function which derivative is that g. And now it's also not so hard because you know how you differentiate polynomials. So now we go to the cubes. X to the power 3 gives us the correct result in the next step. So we can already write down the solution. F of x should be defined as, yeah, okay, I ignore the constants again. We could have minus x to the power 3 and plus x to the power 3. So now you see, if we calculate the derivative here, we get the same as g, just with a factor of 3. And then we get the same as g prime for the second derivative. Yeah, so maybe I write it down, you can do the calculation. And then we get minus 6x and plus 6x. Oh my god, the cat collapsed.
Yeah, this example was just too much.
Too much, I have to go.
Yeah, I think you could also sketch this function just to keep up with this theme of having a sketch of a function that looks smooth in some sense, but yeah, so how does this function look like? So I know how x to the 3 looks like, but now it's once again piecewise defined, and we are once again mirroring the graph on the x-axis for the negative values of
yes.
x. Yeah,
we can just sketch it. Yeah, the chat wonders if the cat is alright. Yeah, she's alright. She just wants to go out, so we let her out. Yeah, we need some excitement here. So now you want to sketch. So this is x to the power 3 on the right hand side. Now on the left, yeah, it's minus, but also negative values. And to the power 3 it's also negative. So it looks the same. It's just mirrored, reflected at the y-axis. So yeah, okay, it's just a sketch. It looks like a parabola. Again, it's not, because it's the power 3, but it's glued together in the middle. And which means in the middle something goes wrong after some derivatives. Yeah, so derivatives work, but then this comes out in the end. Yeah, so go from there to there and to there. Yeah, so maybe now I can put labels to my sketches here. So this is our f, this is our f prime, and this is f prime prime. Yeah, now it works. Yeah, so indeed, these sets we have defined are not the same. Yeah, so you can easily define functions that are only 2 times differentiable or 2 times continuously differentiable. Okay, so this was my first example to get into the mood of differentiation. And yeah, you see, you just have to know here how to calculate derivatives of polynomials. And then you can, yeah, you get the whole example. Okay, any questions left for that? I don't see any in the chat. Fabian?
No, so I think also it's so no questions. There are some examples in the chat that also use the absolute value and piecewise definitions, and I think this is what is also happening here. So you are gluing together 2 functions that work very well, but at the position where you glue them together, something
that's essentially the whole idea. Yeah, and then the other idea, maybe you write it down. Maybe it's not too bad to write it down. Was to have a function. Yeah, what was it? Fabian, you had it in mind. It was the function f of
x. So you can use f of x, but so then I would need to check whether this exponent is right. So I would say you would need something like x to the 5 times the sine of 1 over x. So this would be the value of the function for x that is not equal to 0, because in x equals 0 we would divide by 0. We cannot have that, and then 0 else. And you can see that this is a continuous function, because when x goes to 0, then the polynomial drives it all to 0. And now we need to take the derivative twice of this function and see what comes out.
I think that's a good exercise for everyone. Can check if that works. Otherwise, if it does not work, one has to change some powers here. That was also the idea in the chat. Just choose variables and then see how to choose them after calculating the derivatives. Yeah, so 2 possibilities here. Depends what you know. If you already have some idea about these functions, this is a good approach. If you only know the absolute value, I think this is a good approach as well.
Yeah. So it could as well be that you need an x to the 6. So it depends on how many times you want it to be differentiable and continuous or not.
Yeah, nice. So thanks for that example. And then we go to the next problem, problem 2.
Yeah.
So maybe you scroll up a little bit, then we can see the whole problem. Yeah, that's enough.
Yeah.
Nice.
All right. So now it's getting technical from a different in a different way, because now we want to use, well, the basic definition of differentiable function, or of being differentiable, which is by using a differential quotient. And we now want to calculate derivatives using this basic definition, which is quite cumbersome. It takes some work, and usually we don't need to, because we have already done it and then use some of the rules that we know for calculating derivatives. But here the question is, well, can we also determine the derivative of all monomials x to the n by using the differential quotient? And then in the next one, we will also see some differential quotients, but I think, we leave that for later. So I think it's better if I just make some space here.
Yeah, you start with A,
Yeah.
which is a good exercise. I like it because we talk about differential quotients again, like for the definition, but you do it for all n. So you solve the problem for all polynomials.
Yes. So I think you had it in your definition also before, that being differentiable means that the limit of differential quotients exists. So and this limit, so for one x in R, we call it limit f prime of x.
I would say the differential quotient is already the limit, because usually you say you have this difference quotient.
Yeah, then it's a difference quotient.
And then you take the limit and then you call it differential quotient.
All right.
But it's just a name, because the differential already has it inside that you have a limit involved. You go to 0.
Yeah. Okay, so let's look at this limit of difference quotients. And what we do is, so we want to calculate the derivative at the position x, and then use this x plus h. So h is like an offset of the position where we want to calculate the derivative. And then, so it's called a difference here. So we have a difference of function values, and then we divide it by, our offset h. So I think this has also very nice visual interpretation. This is just the slope of a secant that you can draw to your function graph. Yeah, and this is also where this intuition for derivatives comes from. So we are calculating a limit slope of secants, and if these slopes of secants converge to something, then this is the tangent slope. And this is also why we interpret f prime of x, if it exists, as the slope of a tangent that just fits perfectly to our function graph. All right, so that's the definition. And
that's the definition, and there are already a lot of videos about this differentiability. So if you don't know that so well, if you want some illustrations, some visualizations, you can watch these videos again, and then you can come back for this video where we solve problems. Yeah.
So this this is the definition. So we have not used yet how our problem looks like, and this would be the next part, then to just put in what we know about f. So f is the monomial that is x to the n for some natural number that we consider fixed here. So then I have some x plus h to the n minus x to the n, and I divide everything again by h. And I also need to copy the limit. So sometimes it makes also sense to just leave off writing the limit and just calculating with the difference quotients until one has a nice expression.
Yeah.
Take the limit from.
if you want to be pedantic, I would say it's the correct way to do it, because now you write down this limit is the same as this limit without even knowing if it exists. So this equation only makes sense afterwards then, which is okay. But also for calculation reasons, maybe first calculate the difference quotient without a limit, where everything works, because you also save space. You don't write the limit all the time. So I would suggest to do that all the time, and then just write it again with the limit in the end. But here it doesn't matter so much because we know it will exist in the end.
Yes. But another thing that I want to do is to rewrite this definition in the sense that makes it more accessible for this example. Namely, instead of considering H, also sequences of H that go to 0, we can also consider sequences Y that approach X, and then rewrite, well, this as the limit of Fy minus Fx divided by Y minus X. Or if we plug in our example here, then Y going to X, we would have Y to the N minus X over N divided by Y minus X, because now we see some nice symmetry that we can now use to solve, to come up with a solution. And
maybe you can explain how you go from H to Y. So what is the substitution idea there?
The substitution idea would be to just say, well, Y equals X plus H. Is that the right one?
Yeah, that's correct.
Because if H goes to 0, that means that X plus H goes to X. So, and X plus H going to X is the same as saying, well, Y goes to X. So it's the same, but it's it's a different way to look at it.
It's a different way to look at it, because you send some variable to another variable instead of sending H to 0. But you see with substitution, it's just shifting the problem. You just shift it by the vector X. And that's all. But here it helps. I think this is the better approach because you see the symmetry. There you are right.
So, and now, well, if you have this expression xy to the n, x to the n minus, no, sorry, y to the n minus x to the n, you may recall that there is a formula to calculate this. And I will just give you the formula, because this will now help us. So can maybe later also prove that this formula holds, but for the sake of this solving this problem, so the formula is so for numbers A and B that are different from each other, such that this this quotient here makes sense. We have that this equals the sum going from k to 0 to n minus 1 of a to the n minus 1 minus k times b to the k. So this looks something like the binomial theorem, but it is not. So the binomial theorem always has something here in front, right? They have the binomial coefficient here. And
is it not like the what we call the third binomial theorem from the last video? Like for n is equal to 2.
I think it's a special case
it's a special
of that
case.
one. Yeah, you're completely right. So if we plug in n equals to 2, then we get this this formula that I think many of us know by heart, which is a to the a squared minus b squared equals a plus b times a minus b. So this is contained here, and this is a generalization for it for all n greater or equal than 1 here.
Nice. And you prove that now, or you tell us about the proof?
I would just leave it for the moment. Give you maybe the idea of the proof. So the idea of the proof will be just to show this equality holds by multiplying it on both sides with a minus b, and then using manipulations of the sum, very similar to the ones that you also use to prove the binomial theorem. It's straightforward, but we can see if there are any questions in the chat. We can also do the proof after finishing problem 2a. For the moment, I would just want to use this result. So in order to simplify everything. So let's give it also a reference. So this identity here, I give the reference star. So hope everything fits on the screen now, because now I want to use this identity to modify this difference quotient that I have here.
It looks very similar to your formula.
Yeah, that's great, because now I can simplify everything to a nice looking sum here. So now everything I have is, well, I just interchange a by y and x by b. And then I get this formula of, well, a sum going from k equals 0 to n of y to the n minus 1 minus k times x to the k.
So you just substituted a with y and b with x. Nothing else changed here.
Yes.
Yeah. Okay, so that's simple enough.
So and now I think we come to the point where we see, well, calculating this limit does not have anything to do with differential quotients or derivatives. We are back in, well, in the realm of calculating limits of well, sequences in some sense, or of functions in here.
Of functions, yeah, but the function is just a polynomial in y and x. Okay, in y and x, or just in y.
Yeah,
it's enough.
So we can simplify it in 2 steps here to make it really clear what is happening.
There was a question in the chat if you missed the n minus 1 at the end of the sum.
Up here, yeah. Thank you very much for this remark. So yes,
I think that's important, because otherwise you would have a negative exponent for y.
Yeah,
and you don't want that.
Yes. Yeah, that's very very kind of you to remind me.
Also the next sum.
Yeah. So this is the copy error from here. All right. So now we plug in, or we draw in the limit in here. And we see, okay, so what can we now say about the limits that we have inside here? I think that's all the space we will need. So now let's just look at the limits here.
Maybe it's a good point to say that we also upload the solution in the end.
Yeah, so, we can do that.
I forgot about that in the last sessions, but we will upload all the solutions from the sessions.
So we already have it, or we are producing it right now.
Yeah, so as a PDF, you can also download it as a PDF.
So how about this limit? So if y goes to x, then x to the k, well, is not affected, but y to the n minus 1 minus k, well, just becomes x to the n minus 1 minus k. And why is that? Because this is a monomial, and we know that monomials are continuous. So this is just using continuity. One could use it. One could use this argument here.
You could also say we have the continuity for polynomials.
Yeah.
And then you just plug in.
Yeah, let's maybe just leave this as a remark.
Yeah, so continuity means we already know how to calculate limits for polynomials. We can push the limit inside of the function, and then we can just substitute the variables.
Yeah.
Easy.
All right. So now there is no y left, no limit left. So the only thing left for us to do is to simplify this formula. And one thing that we can now do is by using the laws of powers here, well, to take those two x's together, giving us a sum from k equals 0 to n minus 1 of x to the n minus 1. So and now we see we have a sum that does not depend on k anymore, and we are summing up from k equals 0 to n minus 1, so n times. So this leaves us with n times x to the n minus 1. All right. So coming back to what you said about writing down the limit without knowing that it exists. So the way now we could read it, or we should read it, first would be, well, we start here at the right. So this is something that we come up with, and we now have a justification for every equality that we have here, in particular the one that tells us, okay, the limit is equal to something that is that does not have the limit anymore, and then we just go back until we see, all right, so our function is differentiable, the limit exists, and we can also calculate this limit, and it's the one that we could also have calculated by other rules. So differentiating the monomial x to the n gives us n times x to the n minus 1.
What do you mean by other rules? So how could we have calculated that?
Yeah. So the rule that I usually use for polynomials.
Back.
So, all right. So how do I calculate usually the derivatives of a monomial is by using the exponent here, drawing the exponent in front, and then subtracting 1 from the exponent. So this would give me an n in front and then an n minus 1 here above. So this is the rule that that I usually use. It's way faster, of course, than using a differential quotient, but it needs to come from somewhere, and this is one way to prove it once and for all, to see, okay, that's a rule that holds for all natural numbers.
Yeah, so essentially you have proven the rule you always use now just by using the differential quotient. So very nice.
Could also leave it like that. Yeah.
Yeah, another idea would be to use induction. If you already know this could be the rule, and then you could prove it by induction, because you go through all natural numbers. So it could be a usual induction proof if you know how to do it. But I guess that could also be an approach. Then you don't need to know this nice formula you had there. The formula for the, not binomials, but which looks similar.
Yeah. But then you will also need to know, I think, the product rule.
Yeah.
Maybe. So this could be something that you use. Or I think there's even a way to use the chain rule to calculate this. If you write x to the n, you could also write it as the exponential of n times the natural logarithm of x. Well, then you would need to know what is the derivative of the natural logarithm and what is the derivative of the exponential, and a general rule.
Nice. I like that as well. So it depends what you know. If you don't know anything from the derivatives, just the definition, then this would be the correct approach to prove something like that. Yeah. Of course, you need this star. Yeah, you need to know how to manipulate the numbers, this quotient here, to actually calculate the limit. But if you have seen this for n is equal to 2, you might think, you can generalize that for all n, indeed. So that's very nice. So maybe you can scroll down again that we see this nice star formula, because I think that's something one should remember in some sense, that such a formula exists.
Yes, because it is really hard to get this formula by adding a 0 and subtracting some parts. So I think if you know that something like this exists, then you can just look it up, or if you're in an exam, have it on your cheat sheet, if you're allowed to bring one. Then I think formulas like this are always good to have. And
this is something you would look up to have the indices right. But to have an idea that you can reformulate that as a product, like you have it for the squares, so the a squared minus b squared, this factorization, that you also can do that with more terms in this plus term. That's essentially what it is. To know that, it's helpful. Here you see how you can apply it.
Yes. So we have one question in the chat about using contradiction. So I'm not sure where we could use contradiction in this proof, but I have the feeling that it would not help us too much, because so normally you use contradiction to maybe prove that something fails at one point.
Yeah, I mean, it's a proof of contradiction, like if, how you would use it in a proof for a theorem, for a general statement. I guess that's the idea, but this one is like calculating. Calculating means, yeah, you can't use proof by contradiction to calculate something. Yeah. So there was not like proof this is correct, or it was calculate this derivative.
Yeah.
Yeah. So their contradiction, I think, does not help so much.
Yeah.
Could be, yeah, binomial expansion. Like if you don't substitute with the y, you can also use the binomial formula for x plus h. But then you, more or less, you do the same. Yeah, it's like you want to divide by this h. And this is similar to the formula in star.
Yeah.
But maybe easier to apply. I'm not so sure. Maybe.
I think it's similar, because in the end, what happens here is you will subtract the leading term from the binomial expansion, and then so let's maybe just write down the binomial theorem here for completeness.
Yeah, maybe just do it for
yeah.
x squared again.
Yeah.
I think
Yeah. So
that's
for
good enough.
For x plus h squared, we would have something x squared plus 2xh plus h squared. And if you take in an expression like this, the limit of h going to 0, yeah, then we get again an expression x squared plus 2x squared plus 0. Yeah, so we have an h here.
Why is there a plus 2x squared?
No, we get a 0 here. You're completely right. So
yeah, you
I
want
think
to
we
divide...
need to write down the complete difference quotient to make more sense about this approach.
Yes.
I wanted to show that what happens in the limit is the same as what happens here, but we need the division by h to really see what cancels out and what stays here. So let me modify this quickly.
Yeah, this is what you have with the binomial theorem, but you subtract the x squared.
Yeah.
And then what you should see is that all terms that remain have an h, and therefore you can cancel this h.
Yes, so these two cancel out, and then all the remaining terms have an h. Yeah, and then what remains is 2 times x, because this h will also go to 0.
Yeah, I think with this approach you can prove the formula star if you know the binomial theorem. Maybe. But you can also rewrite it in this sense and do exactly that, just without a limit.
Yeah, so there are different ways, and I would also suggest to try it out, which works best for you, because it may be that you feel more comfortable using one formula or the other.
Yes.
You see that we also do a very detailed step-by-step approach that some of you may find overly complicated or way too detailed, but
yeah, I think, we wanted to show that, how you solve such a problem, and therefore I guess it's needed that we fill in all the details. Yeah, but you see, there are different approaches. So yeah, it's a taste, personal taste, someone writes here, or what you know. Yeah, so if you know some stuff, you can use it, and if you don't know it, then there's no chance that you can use this approach.
Yeah.
But yeah, the result is important. No matter how to prove it, this is what you always remember. Therefore, this is indeed calculus now. If you know the derivative of the polynomial x to the power n, you know how to calculate a lot.
Yes.
Nice. Yeah, I like this problem. Thank you very much, Fabian. But you also have a part B, I guess.
Yeah, this problem comes with a part B. And so again, we want to calculate the derivative. So now it does not say use the differential quotient, but I think from the so now we can see the problem again. So from the taste or the structure of this problem, we may see there may not be another way to approach this other than by the differential quotient. So let's go through the problem text together. So we are given two functions defined on the real numbers, mapping to the real numbers. And one of them is differentiable at one point, x0. So this is the first information. Maybe I underline this also. So this is our first information. F is differentiable in x0. And so the second one information we get is that f evaluated at x0 is 0. And now the second function, g, that we are given is only continuous in x0. So, and I don't think we need that x0 equals 0, but
you chose it as that.
Yeah, I chose it.
Or do you want to delete it there?
I think I can delete it, so it does not matter. So
it's more general in this case.
It's even so. This we don't need. This 0 we really need. So I think it's better if we just leave it off.
Yeah, maybe to emphasize again what happens here, you really use the point-wise definitions of all these notions. So differentiability and continuity are point-wisely defined. There are point-wise properties. So it makes sense to say it's differentiable at one point or continuous at one point. And this is all we use here, nothing more.
Yeah. So, and now the question is, well, we have some point-wise information of f and g. What do we know about the product at this point, x0? Is the product differentiable? And of course, normally if you see a product and someone asks you about differentiability, there's a rule that comes up in your mind. The product rule.
Yes. Yeah? Also, the product rule is formulated point-wisely. Yeah. So it's only if you only know one point, product rule holds for this one point.
Yeah. So the product rule, what it would tell us is if we have two functions f and g from, let's say, from R to R, and they are both differentiable in x0, then also the product is differentiable in x0, and the derivative is calculated by multiplying the derivative of x of f in x0 with the value of g in x0, and then adding the value of f evaluated in x0 times the derivative here. But this rule is not applicable in our case.
Why not? It's what is not given here?
So let's check. So we have the differentiability of f given here, but we only have continuity of g. And we need differentiability because, well, if we look at the rule in here, we use the derivative.
Yeah, the rule already says it in the assumption on the left, but you also see it on the right. The rule does not make sense if you don't have differentiability at x0 for g as well.
Yeah, but so if we look at this rule, we at least may get an idea why this differentiability could still be true for the product, because we have some additional information, namely that f of x0 is 0. So this term here in our example would be 0, so we would not need to care about the derivative of g. But of course, this is just just me speaking. This is not the proof yet, but
it's not a proof, but you say it already. Like, you can generalize this product rule for this case as well.
Yeah,
because I guess in the end you will see that the derivative is exactly the first term there.
Yeah.
Or do you show that? Because it's not given in the exercise. You just show differentiability, but you can also write down the derivative then.
Yeah, this is what we will end up.
Nice.
Then. So I would say let's start. And one general idea I would recommend you, if you have a problem like this, first start rewriting the stuff that I have, for example, underlined here in terms of the definitions, just to make sure that we have everything that we need. So, so let's say this here is our information 1. And this information 1 tells us, so f is differentiable. So this limit of h going to 0 of f of x0 plus h minus f of x. So I'm just writing down again the differential quotient. This limit exists and is equal to the derivative of f at x0.
Yeah, that's what we learned before, but now again in the general context.
Yeah. So let me maybe also write it down like this, because we have a second information here that helps us already to simplify what we see here. Because we know f of x0 equals 0, we can rewrite this differential quotient as follows. So f of x0 plus h divided by h. Yeah. So minus 0. I can just leave out the 0 here.
Yeah, it makes it much simpler. So this is good to use the information immediately. A very nice differential quotient we have there.
Yeah. So what do we have for g? There's also some information. So this is, well, the third thing I want to write down. So g is continuous.
Yeah,
so
g
this
is
means
continuous at the given point, at x0. So you only have information about that, and you only need this pointwise information.
Yeah. So what it tells us is, if I consider a limit, let's say of y going to x0 of g of y, then this limit exists because g is continuous in x0 and it equals the function value g x0.
That's the definition of continuity when you use the limit notation. Yeah, because the limit notation says for every sequence that approaches x0, the values of the function approach g of x0.
Yeah. And now that we are in the setting of differential quotients and we are working with limits of h going to 0, we can also rewrite this. So this would also come up if you just wrote down the proof, but I'm already preparing our proof. So we can also write this down as a limit of h going to 0 of g of x0 plus h.
Yeah, it's the same. It's the same substitution as in the beginning when we talked about different ways to write the differential quotient.
Okay. So I think that's about all the information digested that we have here already. Now let's dive into the actual proof, namely showing that our function f times g is differentiable in x0. And for this, again, I'm going to write down now the difference quotient, and then we'll see if we can take a limit here.
Yeah, maybe one should not forget, you talk about the product of the two functions, which define a new function. So f times g is a new function defined on the whole domain, on whole R, but we just look at one point, x0, for talking about differentiability.
Yeah. So
and that's what you will do now.
Yeah, let's just to be sure write down the definition of f times g. So this is a new function defined on R because f and g are defined on the same domain, which is R, and x just gets mapped to f of x times g of x. So, and this makes sense because f and g are real numbers, we can multiply them. So this is the definition of the product. And now the difference quotient that I want to look at position x0 is the following. So I take some h greater than 0, and I'm looking at f times g at x0 plus h minus f times g at x0, and I divide this by h.
I will ask the question, why do you choose h to be greater than 0? Is it important that's positive?
You are right. So I think it's we should choose it unequal to 0, because of course these limits that we are looking at here, they are considering also h that is smaller than 0. So we could
Indeed,
also look at limits from the left. So it's good remark to make here.
Yeah, you approach from left and right at the same time if you say just x is unequal to 0, and I think that's all you need at this moment to write it down.
Yeah. All right, then let's continue plugging in the definition here. So this means we have f of x0 plus h times g of x0 plus h minus f of x0 times g of x0. So this is the numerator. And nothing changes in the denominator, it just stays h. But now we can start using some of the information that we already know. Yeah, namely f of x0.
That's good.
This is 0 again. So by this was information 2. Yeah, so we can use this again.
Much simpler again. I like that. Yeah. This 0 makes everything compact.
Yeah, but we see that it's vital for the proof to go through. So let's rewrite this difference quotient. So we have fx0. Oh.
Yeah, I've already said that at the beginning. That makes only sense with that the product rule. You need this f of x0 to be 0. So it makes sense. Yeah, it should be vital for the proof. So it's good that you have it.
Yes. So this is all we have now. We can now rearrange it a little bit more. So like this. All right. So, and now let's take a look at what we have shown. So we have namely star and double star, two
can you
two identities
a little bit that we see star?
that we proved earlier. So I think
now
this is a good way to look at it.
And yeah, now you can put both things in.
Yeah, because so by star, now we know that this here converges. So first of all, differentiability also only asks about existence of a limit. So the limit of this this fraction here exists.
And we know it. You have written it in star.
Yeah, it's f prime. Nice. So this one goes to f prime of x0 for h going to 0. And so by star. And this one here, g of x0 plus h, by double star, goes to g of x0 for h going to 0.
Nice. So you have the result.
Yeah. So in fact, we see that the limit. So now let me copy this. So in conclusion, we know that the limit of h going to 0 of this difference quotient exists and equals f prime of x0 times g of x0, which is just the 1/2 of the product rule that we were just talking about earlier.
Yeah, nice.
So our function f times g is differentiable in x0.
Yeah, I think you generalized this product rule now. I like that.
Very good. It's also nice. So you see both you don't need two differentiable functions to differentiate the product when one of the functions fulfills, well, an additional rule. And this is, I think, a good example just to work through again this difference quotient and taking the limits, because in the end, well, you get out a new rule that you can use.
No, very nice. In some sense, the differentiability of f is already enough to make f times g smooth enough at the given point. And then you can also calculate the derivative at this point. Very nice. But you needed all the ingredients here.
Yeah.
So that was already written down in the form that you need everything which is there. Nice. I like that. So is there a question about that in the chat? I don't see anything for us. Yeah, they discuss some alternatives, so yeah, you can do that. But I think this is already a nice proof, because you only use what you know by definition and nothing more complicated than that. And then put everything in, put everything together, and you get the result, which generalizes the product rule. But still, the product rule is important with the in general, as a concept. So don't underestimate the importance of the product rule. It comes in again and again, not only for calculations, also for general proofs. And I would say also, if you do higher dimensional analysis, you have a similar product rule, which you can appreciate if you know this one-dimensional one. Okay, very good. Then I would say we go to the last problem of today, which is my problem. So let's change to my screen here. And so can you see that?
Yeah, looks good.
This is problem 3. Yeah. Yes, calculus. Welcome to the chat. Yeah, thanks for everyone who is here and wants to watch some math problems solved. Yeah, we do our best to solve the problems. And if there are any questions about that, please just ask. Apparently, I need some space here. Can you believe that?
Yeah, so usually these problems don't have a solution that fits in one line.
So now it should work. Yeah, this solution, yeah, okay, I chose that problem for the end, and after your proof, just to get a concrete example in again. Yeah, so
sounds good.
Yeah, it's more relaxing maybe for the end, but you see the function is not so easy, and also I don't want to talk too much about the concrete function, just to apply some concepts here. And you see the concept here is extrema. So we want to find 3 extrema for this function. So extrema, when I write it like that, means local extrema, of course. So locally around a given point, the function is extreme in the situation. So maybe let's talk about that quickly. So this here for the function would be, so in the middle, of course, yeah, this would be a local extrema, a local extremum, namely it's a minimum. It doesn't have to be minimum. It doesn't have to be global in the sense that the function could be smaller here. Yeah, also good. This is a local minimum. And the other one here as well, also a local minimum. So now if you talk about global, yeah, okay, this one is less than the other one, so this would be the global one. But usually when we talk about extrema, we always mean local extrema, because they are important in applications as well. Yeah, you want to minimize, maximize functions in a neighborhood or in some domain you are interested in. And then it might not be important that you have a better one at another point if you're only interested in that region. So therefore, we talk about local extrema. So another one here, you see, this is a maximum. A local maximum as well. Okay, so what is not an extrema? Not an extremum would be like something like that. So there, you also find the derivative is equal to 0. But this is not an extremum. Not local extremum. Yeah, because it's not maximal or minimal in the neighborhood. Yeah, the idea is always, okay, cut the function in a small neighborhood, as small as you need it. Yeah, so here, and then look around the point, and then you see, it's indeed the minimal or the maximal point. And here you see it's always bigger or smaller depending on which direction you go. So this is not a local minimum. So remember that. Looks interesting. Yeah, thanks. This looks like an interesting problem. And it's not so hard indeed. It just gets you to the idea here. What are the extrema we want to calculate? So let's start by finding the extrema in the middle of the function, or not at the boundary points. So these are two things we distinguish now, because in the inner part of the domain, the extrema have a necessary condition. Namely, if we have a differentiable function, and this is a continuously differentiable function, we know that an extremum has to fulfill that the derivative at the given point is 0. So this is the necessary condition for the extrema in the middle. So I can write it down. So we calculate the derivative at x, so general x. And now, Fabian, you might be surprised, but we have product rule involved.
Yeah, because it's a product of differentiable functions.
So good that you wrote it down before, but now we just apply it. So I'll do that very quickly because I don't think this should be the problem here.
That's also the chain rule that we need to in the second part of the product rule, right?
So the chain rule comes in the second part here. Therefore, the cosine of x comes down from the power of the exponential function. The derivative of the exponential function is the exponential function, so no problem there. But the inner derivative from the sine function comes down here. So this is the cosine of x. So product rule and chain rule involved. And also your easy polynomial rule for the first derivative, 2 times x. Yeah, but this is something you will learn immediately when you start with derivatives. Oh yeah, there are a lot of questions. I'll look at that later. Otherwise, you tell me about that if it's important for the exercise now. So we want to find zeros for our derivative here. Zeros means I write, maybe I do it here immediately for the factor x. So I can pull out one factor x here, and I can write it as 2 plus, and there is an x. Funny. The cat is clapping with her ear. I didn't know that she can do that.
Everyone learns something new during these live streams.
Yeah, that's good. I hope everyone learns something here. Okay, so you see what I do here. I just factorize that, what we have, because e to the power sine of x is constant anyway. Or constant is the same in each factor. So I can just pull that out. And we search for zeros. So if we want that to be 0, I write it with an exclamation mark. We want that to be 0. Then we can discuss each part because it's a product. Yeah, so the product is 0 if at least one of the factors is 0. So therefore, this one is never 0 because it's an exponential function, which is always positive, no matter which input it gets. So therefore also the sign does not matter because some exponent putting into the exponential function gives us a positive one. So no problem here. The other one, it's easy. We get this to be 0 exactly at one point. This is 0 for x equal to 0. And no other
you can
point.
just read it off. Perfect.
Yes, but it's only one point. So, but the other one in the middle could also be 0. But I can already tell you this is also not 0. For no x at all. So there's no x you can find that this is 0. And you see that because, maybe we just omit the first part. Here, the absolute value of this second part in this sum, we can say this is less or equal maximum of the x factor here would be pi half.
Mm-hmm.
So, but the maximum of the cosine, what is the maximum of the cosine?
It's 1.
It's 1. It's bounded by 1, so we can just omit it. Maybe I write it as times 1. And then we see this is pi over 2, but pi is at least less than 4.
Yeah.
And so the whole thing here is actually less than 2. Really less than 2. So in the absolute value. So we don't subtract more than 2. So this one cannot go to 0 at all. So in other words, this is also not 0. Yeah, just because we know the domain of the function. Yeah, it starts at pi over 2 and goes to pi over 2. And this is what we use here. So is there a question here? The cat. Yeah, the cat is essential for this live stream. I think so too. Okay. Now we know how many zeros we have for the function, for the derivative of the function, namely only 1 at 0. So f prime of 0 is 0. So a necessary condition for an extremum in the inner part, inside the domain, is fulfilled. And now we have to check if that's also sufficient. So is that really a minimum or maximum, or is it like something like that, where you have the derivative is equal to 0, but you don't have an extremum in the end? So how can we do that?
Yeah, we need to check the value of the second derivative.
Yes, we could do that. The second derivative could get us to a sufficient criterion. I want to avoid that because the first derivative is already very ugly. And for this example, yeah.
You can also just check whether the first derivative changes its sign, which you would also get from checking the second derivative. But maybe we can just read it off because
yes.
We have this nice factorization of yours where already one factor is strictly greater than 0. So this won't affect the sign change. So let's go maybe with the option that does not involve calculating the second derivative first.
Ah, okay. I like your idea because we know that this is also positive. So the sign change would be in the x already.
Yeah.
So we already...
Great.
Yeah, great. This is something you could do. Sign change of the first derivative. My idea was... my original idea was even simpler, I would say, because I didn't want to consider the derivative at all. I just thought, okay, I can check the value of the function at 0. I put it in, and I see it's 0. So, but the whole function here is positive. So the whole function is positive. At 0, it's 0. Yeah, it's positive or
negative. Can you scroll
negative.
up so we can see the whole function
the whole
again?
function again, yeah.
Ah, yeah, because we have x squared, and x squared is also always greater or equal to 0.
So for this function is very nice. So you put in the minimum and see, this is the minimum. There's nothing that can go further down. So something like this cannot happen simply because there's nothing that goes to the negative values. Yeah, but the sign change of the first derivative, also good to see. So we can make a sketch already of the function, if you want that. Which means...
sketch is a good idea, because so we have also in the chat already someone observing that it's really essential to keep in mind the domain of definition of the function when we are calculating this extrema, because this can mess things up. So the argument I think you had with x times cosine of x, this really takes into account our domain of definition. Yeah, because otherwise we could not estimate x.
Otherwise we could not estimate x, yes. But we have a domain of definition which is bounded by pi over 2. So we can use it. Then use it. If it's not like that, you can't use it. Yeah, then you need other arguments. And maybe we have more extrema than in this case. But the function is cutted. Yeah, this is minus pi over 2. This is pi over 2. And the function will not go over these values. So we are not interested in these values. They might be defined in the sense that we can make it bigger. The whole function could be extended. But we don't need to. And we don't do it here for this example. Okay, a plot. Yeah, it starts somewhere here. It goes here to... Yeah, maybe it's more like a whole... Cat is awake again. Essential for this live stream. And then we go to 0 here. Then something happens. And then maybe we end here. So this means the minimum we already checked. Yeah, minimum was here at 0. This is our minimum. But now, if we look at the sketch, this could be also a minimum or maximum. And this could be maximum. So what happens at the boundary is now the question. And how do we check that? So first, this is a minimum. This is the first result. So now the thing is, at the boundary points, we don't need to have the derivative given as 0. Yeah, because the boundary is just cut it anyway. Yeah, so this is a local maximum in the sketch because we cut it here and the derivative could be anything. But if the derivative is negative, we know it goes downwards after the point, so it would be a maximum. So we can just check the derivative indeed at the boundary points to get a solution as we want it. So at minus pi over 2, sorry. So the first on the left. So we put that in. Okay, I copied the function maybe again to the left, that you all see it. I hope you see everything we need here. Otherwise you have to ask. But looks good for me. So this is the function we have. X squared times exponential function of sine of x. And now we put in minus pi over 2. So first we square it. So there's, no, we have the derivative. Maybe
yeah,
I should...
we want to know about the monotonicity, right, of the function.
Yes,
so
yes.
That's why we evaluate the derivative.
The derivative we see still. Okay, very good. Yeah, I wanted to copy both. So maybe I'll just put a box around it. I hope this works.
Because what we know is if the derivative is strictly greater than 0, then we have a monotonically increasing function, strictly monotonic increasing. And if the derivative is strictly less than 0, then we have something that is a decreasing strictly. And this we can then use just as you explained in your chat, in your sketch.
You are definitely right, but I didn't want to go for the whole function. I didn't want to say anything about the whole function, just at a given point. Yeah. So if it's strictly decreasing, maybe it's not so important. We just want a neighborhood around this point. Yeah, we already know, okay, nothing can happen until this point. So very good. But indeed, we can just consider the boundary isolated in this sense. So what is the derivative at the boundary point such that we know in which direction it goes? If it goes strictly down, so strictly decreasing, yeah, we have a maximum there. Okay, now the derivative, we put it in. Yeah, should I write it down? Maybe. We have the first term here, which is minus pi, because we divide the 2, and then we have e to the power sine of pi half, which is e to the power minus 1. Yeah, we have minus.
Because the sine of minus pi over 2. Yeah.
Yeah, I was shortly confused, but we put in minus pi over 2. So we have minus 1 here. Okay, but it doesn't matter. It's still positive. The important part is that we have a negative sign in front of pi. So this is a negative value.
Yeah.
So we have indeed what we have here in the sketch. This is a maximum, a local maximum at the boundary point, because the derivative is is negative at this point.
Yeah, so maybe also note that the second part of the derivative that we have here, the x squared times the cosine, is just 0, because the cosine at pi over 2 is 0.
Indeed. I cut it that short here. But yeah, the second part here is 0, because the cosine of pi over 2 is 0. So this will vanish anyway. Okay, nice. So now I want to do the second part, but maybe we don't see the derivative. Yeah, I just copy that, but now with plus. So now we put in plus pi over 2. Plus pi over 2 means, we also cancel the 2 here again, and this cosine again. Yeah, cosine of minus pi over 2 or cosine of pi over 2 is always 0. So this will vanish anyway. So we still have the first term, and there we just have the opposite. We have pi e to the power 1. which is greater than 0. So exactly what we want on the right hand side, because there, if we have a strictly increasing function, it goes to the maximum, to a local maximum at this point. So this is our maximum. Yeah, so the opposite behavior on the other side of the function. Yeah, but you should see that the derivatives at the boundary points already explain the behavior of the function around this boundary, around these boundary points. Okay, so now this exercise is solved. Yeah, we have two extrema. We have proven that the one in the middle, the one at 0, is a minimum. We already know it's a global minimum. And the two other ones at the boundary points are the local maxima. So, and we didn't use the second derivative, but of course we could have used it for showing that we have indeed a local extremum in the interior of the domain. But the exercise was constructed in this way that we didn't need that. We could just calculate a little bit with the functions. And that's why I chose this function, yeah, that we see it's a complicated function, a complicated derivative, but everything else comes out with easy calculations.
Yeah, so it really helps if you have the ability to also draw a quick sketch to know what is happening with the function, to get a feel for why it may make sense just to plug in a value to the derivative or to the function itself without doing too much work of calculating second derivatives, which you then again need to evaluate.
Indeed, yeah. So you need to know what to do. So therefore, this exercise explains again, yeah, you need the necessary condition if you have a continuously differentiable function f here. Yeah, you can calculate the zeros of the first derivative, but they don't give you all the extrema. They only gave us one. Yeah, so we only found one with this approach, but you wanted to show that we have 3. Yeah, so there, indeed, the boundary was essential. And the boundary could be at infinity, then we don't have a boundary, but here we had it. Here it was minus pi half to pi half. Okay, I think that's good enough for this nice exercise. Or do you see any questions about that in the chat?
So no questions on the exercise you just solved. So I really like that exercise. Nice mix of not doing too much calculations, but doing some calculations.
Yeah, you have to think a little bit. So a sketch helps immediately. So you can always sketch the function at the beginning, how it could look like. Yeah. So you know it starts at some point on the left and ends at some point on the right. So you already know you should check the values at the boundary points to find the extrema. And then you can do the middle. Okay, so that's the exercise here. And I think that's all we have for today about differentiability. But I think we can do in the next session the same again with maybe more abstract problems about differentiability. What do you think, Fabian? Are you up for that?
I'm up for it, yeah. So, yeah, I hope to see you there then.
Okay,
there's more exercises.
There's a question if the interval would be open, or if the interval was open, it would be only one extrema, and that's right. If the interval is open, the function is not defined at the boundary points, so you don't find a local maximum at the boundary point because you can always get closer to it in this sense. Yeah, so that's a good question indeed. That changes the exercise completely without changing so much. Yeah, it just changes that you don't have to check the boundary points, and then you only find the minimum in the middle. Sketch yourself to victory. Yes, I think that's a good approach. Do some sketches and then visualize what you already know and then see where are the gaps. Okay, nice. Then I would say that's good enough for today. And then we meet for the next session, where we also talk about differentiability. I have some
Great.
Yeah, I have some nice problems still about differentiability, so let's put them together and discuss them. Okay, if you still have questions, please use the comments under this video. Check out Fabian's YouTube channel for seeing reaction videos to my functional analysis videos, if you're interested in that. And otherwise, if you want to learn real analysis, I have a whole course, a whole video course you can just watch on YouTube. So just do that, and if you want to see some problems, check out these live streams. Okay, have a nice day. Bye, Fabian.